Hello, everyone, and welcome to Integration of Trigonometric Functions in Calculus. This is a pretty challenging section, but fortunately you are all very smart, so we can do it. The first section is actually just doing trig derivatives backwards. So if you were in class, I would tell you to just get started on them. Just think about what the derivative of what would make sine, and then do it backwards. So if you would like to pause this video and see if you can do them all, that would be great. I've already written the answers up on this screen, so if you would like to screenshot them and see if you can do them, that would be great. Okay, now I'm going to go back and do them myself for people that might have missed one. So literally, I just say to myself, well, the derivative of cosine is negative sine. So since this is positive sine, I must have started with negative cosine. And then, of course, I have to remember to add my plus c. Similarly, when I see an integral of cosine, I know it's going to be sine. But I think to myself, well, the derivative of sine is positive cosine. So this must have started as negative sine for its derivative to be negative cosine. Now, if 4 is a constant, if you want, you can even put it on the outside, so you really don't have to think about it. When I see secant squared, I need to be thinking that came from tangent. You just have to memorize it, but you memorized it going forward, so just keep that same exact thought in your head. Now you do have to make a little switch here. Remember, there's no product rule or quotient rule with integration, so I am going to switch this to cosine. And once I've switched it, then the derivative of sine is cosine, so I don't need a negative or anything. It just works. If there's two things, you can just do them one at a time. So the 3 is a constant, and the integral of sine would be cosine because the derivative of cosine is, oh, it's negative sine. And that's literally how I do these. Plus, the 5 gets to stay, and the derivative of sine is cosine. So I'm good to go. For cosecant squared, again, that's just one that you need to have. If you're in honors, you can just have your list handy and look to see which one cosecant is. It is negative cotangent. It's actually that the derivative of cotangent is negative cosecant, but if there's no negative there, then it must have started out negative. And then sometimes we'll throw in a mix of trig and regular integration. So do what you always do, raise the power and divide. So I raise the power and divide, which gives me negative cotangent x plus x cubed, and don't forget that plus c. On 7, I've already written these answers out, I'll just use this page, but the derivative of cosine would be negative sine, so this must be negative cosine. And the derivative of sine is cosine, so since it's negative, I must have started with a negative sign. This last one's a little hard for people, but it should be on your list. So the derivative of secant is secant tan, so you just have to kind of know this one. Now, I'm just going to tell you right now, there is a list of integrals, and you can memorize this if you want to, and you can write this in your appendix if you're in honors, if you want to. But I will tell you that over the years, so many students have gotten these mixed up because they're so close. I mean, obviously, they're the reverse of the derivatives. So in my opinion, the reason I had you do this exercise is because I think it's easier to just say, well, sine goes with cosine, and then figure out whether or not it's positive or negative. If you try and memorize these, I mean, you have younger brains than me, but it just seems to me that you could get them backwards or get the negatives wrong. So I only have them memorized going from derivative or from the function down to its derivative. And when I want to do integral, I just think about derivatives backwards. I do not memorize this list, but you can do what you want. Okay, so in addition to having to know all your trig derivatives, you're also going to have to know your basic trig identities. So these first 3 problems, practice changing the form using trig identities. So there's no quotient rule or product rule integration. So you're going to have to change this. Fortunately, cosine on the bottom is a secant on the top. And then hopefully you recognize secant squared. If you're using this chart, you can just see that it's tangent. But for me, I have it memorized that the derivative of tangent is secant squared. So I recognize that one. On this next one, I have sine over tangent. Again, there's no quotient rule, so I'm going to have to do a little changing here. I keep my integral sign because I haven't actually integrated. I'm just trying to change the form. I'm going to bring it to the top and make it cotangent. Technically, there's still supposed to be a dx there. And then I'm going to change my cotangent to cosine over sine. You may remember doing these last year, which finally gives me the integral of cosine of x dx. And now that's an integral I can do. Look how I simplified that. That's why we spent all that time on these last year, so that you could simplify complicated, I mean, this is not even that complicated, but so that you could simplify trig identities into something simpler. And again, I think about them backwards. So the derivative of sine is cosine, so I don't need to add any sign, like SIGN signs or anything, and I'm just done. So this next one is pretty hard. If you see a cotangent squared, you might be thinking, oh, that's one of the ones that I should know. But cotangent squared isn't actually on this list. Do I have that somewhere? Yeah, here. Right? It's cosecant squared and secant squared that we know the integrals of. So if you have this one, what you're going to have to actually do is remember this rule. 1 plus cotangent squared is equal to cosecant squared. So these were your Pythagorean identities. Let's just write all three of them so that make sure you have them. 1 plus tangent squared is equal to secant squared. And then the one that most people already have memorized, sine squared plus cosine squared is equal to 1. So I don't actually have just a cotangent, or 1 plus cotangent squared, I just have the cotangent squared. But I can rewrite this as, if I bring the 1 over, then cotangent squared is equal to cosecant squared x minus 1. And I want to do this because, like I said, I know cosecant squared. Cosecant squared does have an integral that I know. So if you're going to put your dx there, you really need parentheses because the dx affects both of them. So I'm just going to do them one at a time. The integral of cosecant, well, the derivative of cotangent is negative cosecant. So since I don't have a negative, then this integral must be negative cotangent. And don't forget that a 1 just becomes an x. So far, all we've done is just rearrange things so that we can do something on our list of 6. This is what I'm going to call it. Your list of 6 is everything. If you know all these, that's going to be the key. But there are going to be 2 types of U substitution that you need to learn. 2 types of U substitution. Here's the first one. The first one is where the angle is anything other than just plain x. You're going to want to change that so it's just u. So I'm going to make this u is equal to 2x, which means that du is equal to 2 dx. Again, that step that I'm going to start skipping is that the derivative of u with respect to x is 2. But then I multiply both sides by dx, and I get du is equal to 2 dx. So in other words, I'm just going to keep moving that dx over to the other side right away. Why would I do this process? Because I want to rewrite this as just cosine of u. I need it to be just cosine of u so I can do the integral. Do I have what I need? I do not. You remember this from last lesson? So I have a dx, but I need a 2. So I'm going to add a 2, and I'm going to add a 1/2. The 1/2 stays. The integral stays. Now it's cosine of u instead of cosine of 2x. And this whole 2 dx becomes my du. And now that I have u's and du's, I can actually do the integration. The 1/2 stays. And I think to myself, okay, cosine always goes to sine. Those two are together. But the derivative of sine is cosine, so I don't need a negative or anything. I'm all set. And once I get that far, then I can put my u back in. Cosine of 2x plus c. Oops, I don't know why I changed it to cosine. Sine of 2x plus c. Okay, let's do another one like that. So my u is going to be 7x plus 5 because I want to rewrite this as just sine of u. That's the kind of integral you're capable of doing. My du would be equal to 7 dx. I don't have a 7 dx, so I'm going to make a 7 dx. To counteract that, I'm going to put a 1/7 on the outside. So I have a 1/7 on the outside. I have an integral symbol. I have sine of u, and then this piece is equal to du. Again, I see a sine, and I know it's going to become a cosine. But the derivative of cosine is negative sine, and I don't have a negative, so this must have started as a negative. So I have my 1/7. I got rid of the integral sign because I actually did the integral. The derivative of cosine of u is negative sine of u, so I feel good about that. And I don't need the du anymore. So the time when the integral symbol goes away is also when the du goes away. Now this is multiplication, so I can move that negative out in front. I can put the u back, and I can add my plus c. If you wanted to check this, it would be so easy. The derivative of cosine is negative sine, so that negative becomes a positive. The 1/7 is a constant. I always keep the angle the same, and then I multiply by the derivative of the inside, which is 7. Those make that cancel, and look what I get, sine of 7x plus 5. Very, very easy to check, but that also means that I expect really awesome grades on this next section. So I'm just going to say right now that I realize that this next one can be done if you've already thought of it using a trig identity. You can switch things around, but I'm going to use this one as a model for how to do a u substitution. So this is the second type of u substitution. That is if you have two trig functions, let the complicated one be u. So in other words, something's being done to cosine. That's complicated. So I'm going to let u be cosine, not cosine squared, just cosine, okay? Not cosine squared, just the cosine, because I can deal with a u squared. U squareds are not a problem. And then my du, the derivative of cosine, is negative sine x dx. This is how you get two trig functions. But what makes this so hard for kids is that when you actually go to do this replacement, all the trig functions are going to go away. And that can sometimes be confusing. So I have a u squared on the bottom. I need a negative sine x dx. I don't have that, so I'm going to put a negative there, and then also put a negative on the outside to counteract it. So this is negative, and then negative sine x dx is du. You can put it on top or out in front, or out on the side. But I am going to change this one more time to u to the negative 2. Remember, there's no quotient rule in integration, so I do have to make it into something that I'm capable of doing. Now see, look at this. This has no trig in it whatsoever, and sometimes people get confused, like, what happened to the trig? This is this is great. This is going to be negative u to the add 1, negative 1, divided by negative 1. There's a lot of negatives here. These two become positive, and that u moves to the bottom. Now I get to put u back, so it's 1 over cosine of x plus c. Or, you know, the worksheets are going to have different answers sometimes than what you think, but you're going to have to be able to look at two different answers and ask yourself if they're the same. Because a lot of times it's just the same answer written a different way. Now I am going to redo number 6 a different way, just so that you can, just so that you can see how this is going to get done. Number 6, if you think of it, then you could have said to yourself, well, sine over cosine, one of the cosines, would be equal to tangent, and let me just cross that out, and then the other cosine could come to the top as secant, and then the integral of secant tangent is just secant. Would this have been faster? Absolutely, if you think of it. Okay, if you think of it, and if you like it. So some people really don't like switching trig identities around. Some people are bad at that, and they really understand the u substitution. But I just wanted to show it to you in case you thought of it. It's not wrong to do it that way. So two different kinds of u substitution. If you have two trig functions, you should be thinking about making u equal to an entire trig function and du equal to the other trig function. If you just have one trig function and then the u is the angle, that's only when you have one trig function. So those are the two types of u substitution that we learn in this section. Now, number 7 is supposed to show you that there's two trig functions that ranks. That ranks over the fact that this is not just x. You still don't want that to be u. Two trig functions ranks over making u equal to the angle. So u is going to be the more complicated trig function. So I have a sine being cubed, and I have a cosine not being cubed. So I'm going to use the sine. It's sine of 2x squared plus 1. Don't let the angle throw you. The derivative of u, so the derivative of sine, is cosine of the exact same angle, it doesn't change, times the derivative of the inside, which is 4x. Now technically this was over dx, but I'm just going to put it over here, right? Okay, so I can see my u. Let's make all the replacements. I'm just going to take this 16 and put it on the outside because I don't need it. You can't put x's on the outside, no variables, but you could put numbers out there and then you don't have to worry about it. So I see sine of 2x squared plus 1, which is being cubed. So I have u cubed. And then for du, I have cosine of 2x squared plus 1, but I need 4x. I just have x. So I'm going to add a 4 to my problem and a 1/4. There is another way to do it, which incorporates the 16 if you like that. So I'm going to add my 1/4 to the outside, and then all of this can be du. So this becomes 4 times the integral of u to the third du. So remember, if you have, normally you would let u be something to do with the angle. Like here, we let u be 2x. We let u be 7x plus 5. But when you have two trig functions, it's more important that u be one of the trig functions, and the angle will just get incorporated. It'll work every time. Remember that u is always the more complicated trig function, but not the complicated part. I don't ever want to make u sine cubed. That would be a mess for my derivative. But I don't mind having the u be cubed, because this is not a hard derivative at all, or integral at all. The 4 stays, it's a constant, and I have u, I raise this power by 1, and divide. So my final answer is u, which is sine of 2x squared plus 1 to the 4th plus c, which of course nobody's going to write it that way. They're going to write it as sine to the 4th of 2x squared plus 1 plus c. This one was super hard. So I understand if you don't quite get it yet. I always tell kids that this is when I used to tutor privately, this was the section where I would get some kids that I hadn't had the whole semester. This is where kids started to lose it. So I understand that this is really hard. Okay, the following examples require integration by substitution as well as the use of trig identities to alter the equation. So these are getting very, very complicated. So first step is I'm going to use a trig identity to alter it because there's no quotient rule. So I'm going to change it to secant squared 2x. And now that I've done that, I do know the integral of secant squared, but I need to, I was going to start to write tangent, which is what the answer is going to be. But I need to let my u be 2x. So du is equal to 2 dx. I don't have a 2 dx, I just have a dx. So I'm going to add a 2 and a 1/2. And now I can rewrite this as the integral of just secant squared u. And then all of this becomes du. You always want it to just be secant squared u, not secant squared of anything else. And if you're thinking, but we didn't do that in this one, well, that's because we got rid of the trig function altogether. We have it just u to the 4th. If you're going to get rid of the whole trig function, it doesn't matter that this piece is not a u. But if the trig function is going to stay, you need it to be just a plain old u. Look on your chart, or hopefully you just know it backwards. The 1/2 stays, the integral and the du go away, and the integral of secant squared is tangent of u. Make sure you put the u back as your final step, tangent of 2x plus c. So sometimes kids say, oh, but you used to always tell us that when we had this, we should switch it to cosine of 2x to the -2, bring it to the top and make it -2. This is a great idea. You can totally do that. But that means you would have to let u be cosine of 2x so that you could make this into the integral of u to the -2, which would be very easy. But do you have du? You do not. You can only make the u, the entire trig function, a u if you have two trig functions, because you need one for your u and one for your du. That's why this method won't work in this case. You're always trying to get something on your list of 6. This list of 6 is key. You have to get something on your list of 6, or if you have two trig functions, then one of them is u and one of them is du, and then you don't need your list of 6 because you've gotten rid of trig altogether. You've written a problem without any trig at all. Okay, next one. So hopefully you're looking at this and saying, all right, I see two trig functions. I'm going to let one of them be u. So u is equal to the more complicated one, but don't include the square. Think about that. If you did the square, don't write this down, then du would be, bring down the 2, secant of x to the first times the derivative of the inside. Is this what you want? This is not what you want. Okay, you don't need to have secant squared be u, just secant. So u is equal to secant of x du is equal to, tangent secant or secant tangent, doesn't matter. All right, well, you might be thinking that's a problem because I thought I was going to make this u squared. But if you make this u squared, do you have what you need? I don't. I need a secant and a tangent. So this is a really funny one. That's why you're going to do a lot of homework on this, because they're all a little different. I'm actually going to have to break this up into secant of x, tangent of x, dx, because I need all of this to be my du. I actually only end up with u du, not u squared. I used one of those two secants to make my derivative. I still got rid of my u, but not in the way we expected. So u is secant, du is tangent secant dx, and this becomes u squared over 2, which becomes either secant squared x over 2 plus c, or 1/2. Really want you guys to get used to this concept that divided by 2 and 1/2 mean the exact same thing. All right, I know that there is at least one of you in the class that said, hold on, why didn't you just do, so I'm going to rewrite it, why didn't you just do u is equal to tangent? Because if you let u be equal to tangent, then you'll have the derivative. The derivative of tangent is secant squared. Well, I'll tell you why I didn't do that. I didn't do that because I was trying to make the point that it always works to make the more complicated one be u. But yes, the green way is a great way to do it. If you're looking for a u and a du, the green is definitely the way to go. So this person doesn't have to do any of that thinking we had to do. They're like, look, I got u and I have du. Do you see it? They're on opposite sides. They're like around the tangent. This and this together made my du. So I have u, du, and I get u squared over 2, which is tangent squared x over 2 plus c, or 1/2 tangent squared x plus c. And now you're hopefully thinking, oh no, we didn't get the same answer. Okay, really important concept here. They are the same. They are. Because do you remember that 1 plus tangent squared x is equal to secant squared x? So tangent squared and secant squared only differ by a +1. So it just means that whatever this c is, it must be 1 more or less than this c, because tangent squared and secant squared are pretty much the same thing, just a difference of 1. Pretty cool, right? Not really, because when you guys go to do this problem and you look at the answer in the bottom of the worksheet and it says secant squared, but you got tangent squared, you can't let that throw you. You need to be able to say, hold on, those are the same answer, because that plus c could be anything. You don't know what that plus c is. Okay, number 10, I see two trig functions. I'm going to let u be the more complicated one. U is equal to sine of 2x. I don't mind that it's 2x. That'll resolve itself. It's more important than when you have two trig functions, u be one of the trig functions. Du is equal to, the derivative of sine is cosine. This is why I don't learn the integrals backwards, because I need to use derivatives within integration. So I just have them all memorized forward. Derivative of sine is cosine times the derivative of the angle. I don't have a 2dx, so I'm going to add a 2dx and a 1/2. And now the 1/2 stays. The integral stays because I haven't integrated yet. I've just changed how it looks. The cosine, the 2x, the dx, and the 2, all of that make du over u to the third. I'm going to move my u to the third to the top and put my du off to the side there. I still need my integral symbol. I didn't actually integrate yet. I'm still just making it easier to do. And now I'm actually going to integrate. So now the one half is still there, it just stays there. Now the integral symbol and the du go away. The du is telling what variable to do things to. I'm going to do things to the u to the negative 3. I add 1, and I divide by that same number. So this is a numerator times numerator, denominator times denominator. I'm going to move that u to the negative 2 down there with that 4, and I'm actually going to move the negative to the top. Most people don't put a negative in the bottom, and that's what it looks like, which is negative 1 over 4 sine squared 2x plus c. Can you check these? Absolutely. If I gave you this and I told you that y was equal to that, I would hope that you would take the 1/4 out, make it sine of 2x to the negative 2 plus c. Then the derivative would be negative 2 times negative 1/4, which would be 1/2 sine of 2x to the negative 3, because we're doing a derivative, we drop that, times the derivative of the inside, which is cosine of 2x times 2. And the derivative of c is 0. These 2's would cancel, and I would get cosine of 2x over sine cubed 2x. So it checks. Oh, that was a... Okay, my pen acted goofy and it's... There we go. All right, next one. I'm going to make u my more complicated one, but not the complicated part, just tangent. So my goal is to make this into u cubed. My du is equal to secant squared dx. This one worked out so lovely. Sometimes that happens, right? It looks so complicated, but if u is tangent, du is secant squared. It's right there, du. This just becomes u to the 4th over 4. So this becomes tangent to the 4th x over 4 plus c. Sometimes you get a nice one like that. Isn't that great? Remember, or you can write it as 1/4 tangent to the 4th x. Try and get used to those two being the same exact thing. All right. That was a little break before the hard ones. Are you ready? This one is especially hard for people because you have to use a trig identity. You have to use the fact that 1 plus tangent squared x is equal to secant squared x, which means that tangent squared x is equal to secant squared x minus 1. That's the only way I know of to do this problem. Sometimes people think, oh, I'll change it to 2 trig functions. I love that. Oh, but it's not cosine. I definitely love when people are trying to think about the way we've been doing this. So sine squared x over cosine squared x. The problem with this is that if you let u be cosine of x, the du would just be sine of x. It wouldn't be sine squared. So you'd have this extra sine lying around. But if you thought of that, that was still a good train of thought. So I'm going to rewrite this as secant squared x minus 1. I do need the parentheses around it for the dx. And now I can do them one at a time. The integral of secant squared is tangent of x, and the integral of 1 is just x. So this one isn't hard in the end, but I'm going to just tell you right now, it comes up on a test or a quiz, and it is one of the most missed because people forget to do this. Okay, 13 and 14 have a special rule. If you are in honors, yay for you. You get to write this in your appendix. If you're in AP, I'm sorry. It's not like I make up these rules about memorizing everything. But here's what you need to know. Cosine of cosine squared x is 1 plus cosine of 2x over 2. If you're thinking, we learned that? We did. We learned it, though, this way. If I clear the fraction, 2 cosine squared x is equal to 1 plus cosine of 2x. And if I subtract the 1, maybe now it looks familiar. Okay, it was one of the double angle laws. So you learned it this way, but that's not helpful to us. So in calculus, we rearrange it, and this is the only way to do sine and cosine. For sine squared x is equal to 1 minus cosine of 2x over 2. So these are the two that you want to have memorized or in your appendix. And then this is actually still a really hard problem. So let's go ahead and change this. Personally, I'm going to take the 1/2 out. That's why I've been trying to press this point. Divided by 4 is the same as 1/4, right? So I can take this 1/2 out. 1 plus cosine of 2x. I'm just going to take it out of the integral completely and not even worry about it. So if you want to stop the video and see if you can do this pretty basic trig function on your own at this point, you can, but I'll see you in a minute when you get the wrong answer. Oh, I guess you want the answer. So the answer is x over 2 plus sine of 2x over 4. I would love, love, love for you to get this correct, but I regret to say you will probably be back, turning your video back on, unpausing it to watch how this is done, because you probably won't get that. Okay, so let's do it together. So there's two ways to do it. The most common way is to let u be the angle. There's only one trig function, so u is going to be the angle. U is equal to 2x, so du is equal to 2 dx. So remember that there's parentheses. I've been saying that all along and then forgot to write them. There's parentheses around that. I don't have a 2 dx, so I'm going to add a 2 to the problem and another 1/2. So be really careful. That 1/2 has nothing to do with this 2 out here. That's why I made them in green, so you could see that. And now I have 1/4 the integral of 1 plus cosine of u du. Isn't that better? Again, this 1/4, not to worry about it. I'm actually going to do the integral now, so the du and the integral symbol will go away, but I do need to keep my parentheses because that 1/4 will affect everything. Okay, this is where if you're watching this video, you probably went wrong. If you wrote x here, you made a very common mistake. The integral of 1 is x if you're doing things with respect to x, but I'm doing things with respect to u. So this becomes u, and this becomes sine of u. You see that? Let me just check that. The derivative of sine is cosine, so that's right. So this becomes 1/4, and then u is 2x and sine of 2x. This little step right here is where you need to watch out. And then plus c. Or if you distribute the 1/4, you'll get x over 2 plus 1/4 sine of 2x plus c. Or the way I wrote it, over 4. All of them are correct. So many correct answers. Okay. All right, if you would like to try number 14 on your own, the answer is x over 2 minus sine of 2x over 4. It is really just another chance to practice what we just did because it's almost the same. But it's also, for me, a chance to show you a different way to tackle it. So a different way is, first, I do have to, I'm still going to take that 1/2 out. Regardless of which way to do it, that's still the best move. Dx is to make it two separate integrals. So 1/2 the integral of 1 dx minus 1/2 the integral of cosine of 2x dx. This is another alternative, is to treat them separately. And then this one really does just become x. The integral of 1 is just x, which is how we're going to get x over 2 in our final answer. And then you only do the du on this one. U is equal to 2x, du is equal to 2 dx. This one needs a 2 and a 1/2. So this piece of it becomes minus 1/4 integral of cosine of u du, which is negative 1/4. I'm actually going to integrate now. The derivative of sine is cosine, so sine of u. And then I can put my answer back, minus 1/4 sine of 2x plus c. That's where that comes from. So two separate integrals is another way, which honestly, whichever way makes the most sense to you. But 13 and 14 traditionally considered very, very challenging problems. 15 and 16 also have a little bit of a trick to them. If you would like to pause and see if you can figure out a little bit of a trick, you can. So you can't let u be equal to sine of x, even though that would be such an easy problem, because you don't have a du. The du would be cosine of x, and you don't have a cosine of x in this problem. But if you don't have two trig functions, and sine cubed is not on your list of 6, right? You can only do integrals with trig functions if it's on your list of 6. Then you have to figure out some way to change it. So either you do have two trig functions, or you make it into something that looks like on your list of 6. The key is to rewrite this as sine of x times sine, yeah, I do want that. Sorry. Sine squared x, and then dx. This is going to be 1 minus cosine squared x. So do you remember this one? Sine squared x plus cosine squared x is equal to 1. So I can replace the sine squared with 1 minus cosine squared x. How does that help me? Now I have two trig functions. Which one's the easier one? Definitely the sine is the easier one. Definitely the cosine is the harder one. So even though originally I was going to let u be sine, I actually want u to be cosine of x. Du is negative sine of x dx. I don't have the negative, so I'm going to put the negative in and put a negative on the outside to counteract it. That negative has to stay there, but this negative, this sine, and this dx are all my du. So I have 1 minus u squared du. This is another chance for you to practice this concept that when you do this integral, this is going to become u, not x. U minus u cubed over 3. Du tells you what variable is part of your equation at this point. And then this is distributing it, negative u plus u cubed over 3. And since u is cosine, the final answer is negative cosine of x plus 1/3 cosine cubed x plus c. I will write down the answer for the next one, which is extremely similar. Sine of x minus sine cubed x over 3 plus c. All right, and I will do this one slightly differently so that you have options, and hopefully one of the ways will make sense. But the first step is the same. I'm going to change it to cosine times cosine squared. And then using the same rule up here, Now I'm going to get cosine squared all by itself, which would be 1 minus sine squared. All that trig. I know you thought I was just trying to torture you last year, but I hope you see now I really had your best interest at heart. You never could have done this problem without the trig we did last year. So now another option is to break it into two separate integrals. This is going to be, if I distribute the cosine of x minus cosine of x sine squared x dx. So slightly different tact here. I'm going to do the integral of cosine of x minus the integral of cosine of x sine squared x dx. This one can just straight up be done. The integral of cosine is sine. This one requires u substitution. U is sine of x, du is cosine of x dx. So this is u squared du, which becomes u cubed over 3, which becomes sine cubed over 3. There's a negative on the outside that stays, and I have sine cubed x over 3 plus c. There's a little x there, forgot it. So I know it looks like we have two more, but we actually don't. These are just two little challenge problems. I'm not even going to give you the answer. But if you feel like trying to figure them out, they are just problems that I always have in class for kids that maybe are pretty far ahead and feeling like they've got this and they don't need any more practice. Then this is usually something that kind of stops them in their tracks. So if you're feeling a little challenged and you would like to do these, go for it. You can email me the answers and I'll let you know if they're right. All right. You have a great day.